In this lecture, we will look into some more sequential circuit design problems, and these are some standard, very standard problems which are asked to make a circuit of. These are called the pattern detectors. What are the pattern detectors? So it's like you suppose there is a system. So this is the pattern detector. There is a system and some input is coming and you have some output. So input is like a string of bits. So you throw some bits into the system. So you throw some bits into the system and the system will try to identify a pattern in the coming input bits. So if it recognizes a pattern, then the output would indicate that a pattern has come. Okay. Otherwise the output will not indicate anything. So that is the thing. So here pattern detector, as you can understand, it can be any pattern. So there is no limit in asking what the pattern you want to want to detect, right? So it can be many different types, but the idea of how to develop the pattern detector, that is important. So you should take that idea, and then any pattern you are asked to detect, you will be able to solve that problem. So here we are trying to detect the pattern which is 111 sequence. So if 111 comes in the input, anywhere in the input is the string of bits are coming, when 3 ones come one by one or one after another, when 3 ones come one after another, then we recognize that the pattern is there and we have detected that pattern. So what the circuit has to do? The circuit has to keep a track of the input bit stream. This is the first thing. It should keep a track. It should remember what are the previous bits that has come, and along with it, when the present bit now comes in such a way that the total string is completed, total pattern is completed, then the output would be made high, or it should indicate the output should be made active. Now there are two different types of pattern detection. One is with overlapping and another is without overlapping. What are these with overlapping, without overlapping? Let us understand with an example. So here you see a pattern, a string of bits u coming in the system. So this is the first bit that comes in 0, then another 0, then 1, then 1, then 1, then 0, then 1, then 1, then 0, then 1, 1, 1, 1, 0. So like this, a pattern, a string of bits are sent to the system. What would be the output? So this each bit is coming in each clock cycle, that one has to understand. One bit is coming in this clock cycle, in the next clock cycle the next bit is coming, in the next clock cycle the next bit is coming. So at each clock cycle we have to notice what is the output. So that the first clock cycle, obviously the output would be 0, then again 0, then 0, then 0. Now at this clock cycle you see the pattern is detected, 1, 1 and 1. So the output should be 1 at this clock cycle. Then again it is 0, so the output again should go to 0. So like this it is happening. So 1, 1, 2 ones are not giving any output. Now again a 3, 1 is come here, output has come. What about the fourth one? So this is the overlapping nature. Overlapping nature means it continues the detection. So once a pattern is detected, it does not reset itself. It continues with the detection. That means when this one comes, it will again see whether I have 2 ones previously or not. It will again see that. It sees that you have 2 ones previously also, then again a 1 would come here, and then again a 0 is coming. Without overlapping means when it has detected a pattern, then it resets itself. That means it starts detecting pattern freshly again. So these two ones will not be considered anymore So it will start detecting the pattern afresh, starting from this one. It will start detecting the pattern afresh. So if there was one, if there was a one here and another one here, then at this position you will get a 1 again. 1 0 1. Yes, this is the without overlap, where it restarts the detection. So let us try to develop a circuit for the pattern detection of 111 sequence. Let the first very important step is to identify the states. In such pattern detection problems, you should always keep a state reserved for the initial state or the reset state. Reset state means you are counting, but suddenly the count becomes lost because the pattern is broken. Whenever the pattern is broken, you should again start counting. You should again start looking at the pattern afresh. So that is the reset state where you should go when the pattern gets broken. So 1 has come, so you are waiting for another one, but a 0 has come, so the pattern gets broken. 1 1, then again a 0 is come, the pattern gets broken. So you should go to the reset state whenever such thing is happening. So one state should always be reserved for the initial or the reset state. Initial and the reset state both are same. So S0 we reserve for the reset state. This is a state whenever a 0 is detected. S0 is a S0 is a state whenever a 0 is detected. So whenever a 0 is detected, the pattern gets broken. That you understand. So that is the state. Then S1 is whenever a single 1 is detected. Let us define this state S1 when a single 1 is detected at the input. S2 is whenever double 1 is detected, one after another. Consequent ones, 2 1s are detected. S3 when triple 1 is detected, and then this state produces the high output. When this state happens, it produces a high output. Otherwise, there is no output in the other states. We need only this much. We don't need S4 which is 1 1 1 1. We don't need that. Why we don't need that? When we look at the state table, you will identify. You will be able to understand. Let us look at the state table. Before that, we also define the S0 in terms of binary. So since we have 4 states, we can use 2 flip-flops, and the binary words associated with the states are given as this, which are very intuitive and corresponding to the number, decimal number actually. Now you look at the state table. So when you have this is S0, this is also S0, this is S1, this is S1. I am writing for your convenience, but once you have defined the states, there is no more need to write. So S0. So when you are at S0, what does that mean? It is initializing or the sequence has broken. At this time, if you are receiving a 0, where would you go? You would remain at that S0 because you are not detecting a sequence, any one has not come. So you can draw the state machine diagram. It is asked to draw the state machine diagram. Let me help you out here. So there are 4 states, S0, S1. I believe this is a mood state table. So you can associate the outputs also. S2, sorry, this is also 0. In S3 you will get the output when 3 consecutive ones has appeared. From S0, this is the initial state, so you can have an arrow like this which indicates the initial state. Now from S0, if you have 0, then you are actually coming back to S0. You are not going anywhere. But if you are having a 1 as input, then you are going to the state S1 because a single 1 is detected now. From S1, if you are having 0, then you are going back to S0 because the count is broken. So you see here from S1, if you are having U is 0, you are going to S0. This is happening for each of the states actually. If you are having 1, then you are going to S2. From S2 also, if you are having 0, you are going back to S0. And if you are having 1, then you are coming here in S3. And then you are at S3, you are actually, when you are at S3, you are actually having an output 1. So you see in these two rows of S3, the output is 1. And from S3, if you are having input 0, then you are going to S0. If you are having input 1, then you are remaining at S3. This is the case of continuous detection, mind it. So this is a case where 1 1 1 another 1 is detected, so you are continuously detecting. In this particular count, you are again detecting that you are in state S3. Here also you are detecting S3, now also you are detecting S3, and hence you will again come back to S3 and generate an output because you have come back to S3. In case this was not a continuous detection, or it was without overlapping, then what would happen? After coming to S3, no matter after coming to S3, if it was a count, if it was a pattern detection without overlapping, then from here the 0 is same. So I write with blue, the 0 is this, it would go to the S0 state, but with 1 it would come to S1 state with 1. I hope you understand this. Okay, so that is the situation here. So once you have got got the state table, you can now find the next state equations and the output equation. The next state equation and the output equation are solved for you. I hope this solution is correct, so you please check yourself, and then you have to draw the sequential circuit. Then you draw the sequential circuit. So since the equations are here, let me try to draw the sequential circuit. Let us see. So when you are drawing the sequential circuit, mind one thing, you know how many flip-flops are there. You know that there are 2 flip-flops. As many flip-flops are there, you draw the flip-flops first. Draw these squares and draw them with some distance in between, because you don't know what logic gates combination circuit you have to place in between these flip-flops, so keep some distance between them. Now you start to draw. So I am drawing D flip-flops. So this is the flip-flop number A, Q bar. This is a flip-flop number B, Q bar. So what is your QA plus is U and QA plus QB. QA or QB, and this has to be ANDed with U, which is going to D. So a U is here, U signal is here, and that is going here. What is QB plus? QA or QB bar. So QA is here, it has to be ORed with QB bar and then ANDed with U. Okay, let us first do the QB bar. I have taking here, I have to OR with, so so let me take this a bit more on this side. So I have to OR and with it I have to and what, and the u, right? So you have to take from here. So you see, while drawing I am using the loops, right? So always use the loops while while drawing. So this is what makes your dB. Y is what? Y is simply QA QB. QA and QB is odd here, so let us take this and it, get Y, so the AND will come with a QA. So now your circuit is complete. Is it complete? No, it is not complete. One thing we have not given, and this is a mistake for which your marks will be deducted. You have to give the clock. Please remember this. You have to give the clock input to both the flip-flops. We don't mind whether your flip-flops are positive edge triggered or negative edge triggered, but they should be consistent. If you are using positive edge triggered, both should be, all of the flip-flops should be positive edge triggered. If you are using negative edge triggered, all of the flip-flops should be negative edge triggered, because the output should change at the same instant. That is the major thing here. We are developing synchronous sequential circuits. We are not developing asynchronous sequential circuits. With the steps that we are following, we are always developing synchronous sequential circuits. It is not mentioned anymore, and the clock has to be supplied to each of the flip-flops like this. This is implicitly assume that you are doing this. You have to do this. So please take care of that. If you are not giving the clock, you will not get the full marks for the design. Next we will see another example, which is the detection of 101 sequence. Again the same thing, the circuit, we have to keep track of the input stream. Whenever the 101 is detected, we have to make the output high, and the circuit has to work with overlapping. Okay. So we define the states S0, and here we have already noted down what it would be in binary. The binary count is also noted down. So S0 is the initial state, and whenever there is a break in the sequence, we would go to S0. S1 is when a single 1 is detected. S2 is when 0 happens after 1. So 1 is followed by 0. So the 0 detected at the input when the state is already S1. So now I think things are getting clear in your mind how you are actually you will be able to draw the state diagram of the state table. So S2 is you are going to S2 when a 0 happens at the input when you are already in S1, because S1 is defined when a single 1 is detected. S3 is 1 followed by 0 followed by 1. That means 1 is detected at the input when you are already in S2, and this state produces the high output. Okay, so with this understanding of the states, now we can draw the state diagram as well as the state table. The state diagram is drawn here, you see, as per our sequence detection. So you just read the state diagram once. So let us look at the state diagram. S0, from S0, this is the initial state, so we can give an arrow actual also here in initial state. So when we have a 0, we come back to S0, right? When you have a 0, we are not starting the sequence actually. When the 1 is detected, then we go to S1. From here, if a 1 is detected, we again remain at S1, because we are again waiting for the sequence to start. As many 1s are detected, we will remain at S1. Only when a 0 is detected from here, we will go to the next state, S2. And at S2, we will wait for a 1 to happen. But here, if instead of happening 1, a 0 happens, we will again go to S0 because the sequence gets broken. 1 0 0 means sequence gets broken, and then again it will start again. From S2, if I have a 1, then I will go to S3 and I will generate an output when I am in the state S3. From S3, if I am having a 0, then because of overlapping nature, I will be now counting it as 1 0. 1 0 I will count, and that is the state S2. So I am going to S2. If I am getting a 1, so 1 0 1 1, that means a single 1 has been detected now, because 1 0 1 a sequence has been detected. Now again if a 1 comes, it is a single 1 detected, so it will be the state S1. You will go to S1. In this way you have to complete the state diagram, and then you can write down the state table. When you are drawing the state diagram, please be careful in one thing. Just note whether you have given all the inputs to a particular state or not. So if you recheck that, your state diagram would be complete. So there should be two arrows coming out of each state, one for input 1 and another for input 0. Now look at the state table. The state table has been drawn. So you can see that this is how the movement is happening as per the state diagram. The state table is also giving the same information. One thing to note, that the output is 0 for all the states except S3. In S3 it is 1. This is a Moore machine because the output depends only on the present state. This is how the system is being designed. From here you can write it in terms of the binary words. So you will get QA QB, QA plus QB plus. Then you can make the next state and the output equations, which will be like this. So you derive the equations. I am just providing it here just for cross reference. So this will be like this, and you can draw the circuit after that. This is the Moore machine. Moore machine, why? We have drawn up the state table in such a way that the output comes only with respect to a particular state. However, this same problem can be designed in terms of a Mealy machine also. How would it be? See the Mealy machine. Here we are saying, note this, we are saying that the output will come when you are at S2, that means 1 0 is detected, and then a 1 is detected, then your output becomes high and you go to S3. In this way we are talking now. In this way we are talking. And in the state diagram also you see it has become a Mealy diagram. So when output is only in this particular case, no other case has an output. So when you are going from S2 to S3, because a 1 has happened, at that instant your output is also becoming high. Now the entire formulation becomes a Mealy formulation. It is Mealy because you see that the output is not consistent over these states, over the state S2. Now you can again reformulate. So your state table is already reformulated in terms of Mealy, and you can like draw up it in terms of QA QB QA plus QB plus, and then find out the next state and output equations, and it will be a bit different than Moore. However, the output that you will obtain will remain the same. The behavior will remain same. Behavior of the system will remain same. This is the system. So what we understand from this very good example of pattern detection is a very fundamental idea that you can actually design a system in terms of Moore as well as in terms of Mealy. It is entirely your choice, entirely your convenience. Also, there is lot of flexibility actually, because you can express the states, the binary words you are assigning to the states are also in your hand. But whatever way you have defined, proceed in that manner. That thing one needs to keep in mind. If you are designing in terms of mood, proceed entirely in terms of mood. If you are designing in terms of milli, proceed entirely in terms of milli. If you have denoted S0 as, instead of 00 you might denote as 11 also. Proceed in that manner entirely, otherwise you will mix things up. So the best convention I have given in the discussion in these lectures. This is the most simplest convention. Everywhere in any textbook and any reference material you will see this convention. So you should also adopt this convention. That is the thing I needed to say. So thank you for your attention, and there are one or few more topics. So this is the examples are completed. So this sort of examples you can expect in the exam. There are some more understanding we need to do on the sequential circuit design, that will take up and that will come to the end of the course. Okay, thank you for your attention.